Hello everyone. Now, I know it has been quite long since I've uploaded any videos on problems or let's say some DSA problems, but now here I am. This is not exactly a DSA problem, it's more like a beginning problem to AI/ML stuff. So, this is from one of the courses that I'm taking by Dr. Munideepa ma'am, and it's a beginning of AI course. Okay, so we are given two jugs. One may be a 3 liter, one may be a 4 liter here in this case, or it could be some 3 liter and 5 liter combination. And you have to go to some other states. Okay, so the problem is like this: you have a 3 liter jug and you can fill it up to 3 liters because you know the demarcation up to 3 liter. You don't have any other demarcations. A 4 liter jug, you can only fill up to 4 liters. You don't know where it could be a 3 liter point or where it could be a 2 liter point. Now, the point is that you need to fill up these two jugs by either fill it up from an infinite faucet or just dunk the waters into somewhere else, such that you get to some particular filled condition of one jug. Here, in this case, the 4 liter jug containing 2 liters of water. Now, you could do something like, okay, I fill up the 3 liter jug and I dunk it into the 4 liter jug. Yeah. So you now have a 4 liter jug with 3 liters of water. You know that you filled it up exactly 3 liters. You don't need any demarcations to help you with that. Now, other times I would have just gone directly into the programming, but even though I might have just 30 viewers, I got a few feedback that I should also explain the reasoning behind going into writing that program. So here in this case, it will be the first video of, let's say, 1 or 2 videos where I shall be explaining the concept behind, though it has already been concept in our courses, but it's a very popular problem. Let's just try to solve the algorithm, solve this problem with the 3 algorithms that has been asked. The 3 algorithms in this case are BFS, DFS, and ID-DFS. Now, these are actually the graph search versions that we shall be using. And you in graphs, what do you have? You have points or vertices and edges. So you need to connect those edges. Okay, but in this case, this is mostly like a tree. It's actually like a graph because you can do backtracking. Okay, in trees, like in the previous semester videos that I've uploaded, we could not do this backtracking. Okay, now we have that ability to basically go back to a certain state. Now, let's get right into the algorithm. Okay, let's first understand that what the 3 algorithms even mean. Hopefully this font is visible enough. I'm using VS Code because just I like the UI. I know I hate the Electron stuff, but it's just the most familiar and it has a lot of tools. Okay, so whatever. Now, the first thing that I've written is the breadth first search. That's your BFS. Now, this is like a level by level explorer. It's more like your isekai explorers. Okay, now the main idea or the philosophy is that now you have suppose a tree. Okay, in that tree or in that particular graph, you basically search the first level. Now, it might be very much difficult to understand. A good analogy that I have given you is, suppose you are there in your school and you want to find your friends. Okay, now you probably are new to the school. You just got admitted, like a lot of the master students just got admitted. Now, what should they do? They would first search the whole floor. Say you are on the first floor and you will search the first floor completely to find your friend. So if you are not able to find your friend, you go to the next floor. So this is like breadth first search or a level by level searching methodology. Now, here you need to understand that it uses a queue data structure. Last course, we did a lot of queues. We did priority queues and all this. And this is a first in, first out system. You are just basically in a line. Suppose there is a bakery and you want to get that cake. But because you want to get that cake, you have to be in a line. And the first one in the line will get that cake first. This is the queue algorithm or the queue data structure that we use. Now, you then add the starting state to the queue. So now what this state means? You might be very much confused that there are states and the state of a machine, state of thermodynamics and all this. You might have read state variables, but state in computer science basically means a snapshot of the system. Now, in this snapshots, it captures how the system is at that particular point in time. So suppose you have something like 3 liters completely filled in a 3-liter jug and 0 liters completely filled in the 4-liter jug. In that particular case, the say your first index, or the let's say your 0th index represents the 3-liter jug and your first index represents the 4-liter jug. How many liters of water do you have in your 3-liter jug? Or at index 0, it's 3, and how much you have in your index 1, it would be 0. So it will be 3, 0 state. In that way, you track the variables, or so not variables, the state of the system. Okay. Then you loop take the first item out of the queue and check if it's the goal state. The goal means, according to this problem, would be 4 liters jug containing 2 liters of water. Now, it also asked me to create some kind of like this GIFs or this animations that I've created. So, just like every other thing, even though the course asks us to do it in Python, but Python abstracts away a lot of the minute details. So I would rather do it in C. But let's see. Let's continue. Now, the key characteristics of a BFS algorithm is that it ensures completeness. If a solution exists, then the BFS is guaranteed to find it. And understand that it will always find the shortest path, the one with the fewest steps. So it might be like you go to that particular condition after trying out a lot of different states, or a lot of different filling up and dunking the water in some way. But the BFS kind of guarantees that it will find the shortest path with the fewest steps first. This is this is the greatest strength of this. But remember, it means that you need to waste a lot of time exploring the first floor. Then you need to go to the second floor. If your friend actually exists in that building, then you are guaranteed to find it. He might be at the top floor, but reaching to the top floor, it will take you time because you are exploring each and every floor one by one. So that's where the caveats kind of begin. Now, let me show you one mermaid diagram that I made. So this is for no, this is the water. There is the BFS. This is the DFS. This is the BFS diagram. So yeah. Let me just close this. This is the BFS one. So now let's start. First, we have the condition where you don't have anything. Then you fill up the so first in the 0th index 0,1 0,0. So the 0th index represents your 3-liter jug, and the first index represents your 4-liter jug. The second index, as you can see, I filled up the jug, 4-liter jug first. Then I basically dunked the water of the 4-liter jug exactly to fill up the 3-liter jug to the brim. That means I know that 3-liter jug is filled to the brim. That means it will contain 3 liters. The 4-liter only has 1 liter in it. Then what I do? Then 1 liter in it. Then I totally dunk the water of the 3-liter jug into some garbage or into the sink. Then I am left with the state where I don't have any water in the 3-liter jug. That means it's 0 and 1 liter in the 4-liter jugs. After that, what I do? I basically dunk the 4-liter water, like whatever the water in the 4 liter is 1 liter into the 3 liter. So I have 1 liter in the 3-liter jug and 0 liter in the 4-liter jug. And I just continue this process where I again fill up the 4-liter jug. So I have 1,4. And now what I basically do, I dunk all the remaining water in the 4-liter jug into the 3-liter jug, because 3-liter will have an empty capacity of 2 liters. I filled the 3-liter completely, but now I have 2 liters in the 4-liter jug, which is my goal state. Now, how the algorithm works, you basically start, then you initialize a queue and visited list. So that list will contain which particular states we have already visited. Then we will start the node at 0,0 and we add it to the queue. So the first question that we ask, this is one of the main questions that we ask, is that is the queue empty or not? So suppose it is actually is not empty. Okay, then only we will go. Suppose it is actually empty, means that currently there is no problem. The solution either has already been found, or it needs to be basically, it doesn't exist. Okay, now you first do a dequeue of the state. The initial states is already added, so of course the queue is not empty. Then you do a dequeue of the state, and what you do is, okay, so I think I should have mentioned it properly, which is, yeah, there should be an arrow to here. So okay, fine. So after you basically dequeue the state, you then check for the goal. Okay, I should have mentioned it in this case that we are looking for the goal. Is 0, 0 the goal of our like algorithm? No. So right, then we going to generate the neighbors. Okay, generate the neighbors means we are going to look for the neighbors. Now for each neighbor there may be more neighbors. Okay, now we need to check that have we visited that neighbor or not. If we have already visited, then we look for the next neighbor. That means in a level we are looking for each and every, let's say, room. So the first room I checked and I found that okay, like have I visited this room? The point is that no, I have not. Then let me check. Is there the state that I'm looking for? No, it's not. Then I will go to the next room. Now suppose I've already checked the next room, then I need to basically check the next room to the next. Okay, and suppose I haven't visited that room, then it will be added to the visited list. Now then we go backtrack and basically go to this for each neighbor, and we basically find each and every neighbor. Now the point is that suppose we are unable to find the goal state in all the neighbors and there are no more neighbors left for me to check, then that means the solution does not exist. Okay, this is the simple BFS algorithm. Let me go back to here. Let me show you the pseudo code for it. I think I should have it in a preview mode. Yeah. So it should be here. Yes. So you first create a queue, you like create a list to like track the visited states. Then you start the state with the values 0, 0. Then you add this start or the beginning state to the queue. And then you add the start state to the visited states because you have already visited that state. Unless and until it's such a trivial situation where your jugs need to be empty for it to work. But yeah, you can add that visit. Like generally these are not, but yeah, you can just check that as well. Okay. So now the point is the main loop. So the main loop needs to continue as long as there are states to explore. That means we are, this is a very important point though. As long as there are states that are still left for me to explore, like if there are floors in the building and I haven't gone to each and every room of that floor, that means more and more states are left for me to explore. Now this loop will continue while the queue is not empty. That means the queue for the states is not empty. Now then first what we need to do, we need to basically check the like remove the state or remove the first item from the queue. So I have a list. So room 101. Have I visited it? The point is no, I have not. Let me visit it. So I visit it at first. That means it is cut off from my list. Like this is cut off from my current state. I am there right now. I am there. Now the point is that is the current state is my goal state. I look at it to find my friend. So no, the friend is not there. If the friend is actually there, so you will find that I have done the goal checking first because this is generally how it's done. First, you first check that is the friend there or not. And if it is there, then you just reconstruct and print the path from the start state to the current state. Basically, you just narrate the map where to find your friend. Then you generate the neighbors, which basically means, okay, the friend is not there. So I have to go to the next room. So I go and you do it for each possible action, that is fill and empty and pour. Okay. And you continue this action for each and every like function, not yeah, I can't say this as functions, but these are actually actions that you can do. Basically you can go into a room and check for your friend. Okay, but here you can do it for fill a can, you can dump it down, empty it out, you can pour one can's content to the another can or another jug. Then you basically add to the queue if this is a new state. Okay, only explore this new state if we haven't visited it. Means you also have to check that from the visited list, have you already visited it or not. Then you add the, suppose then again this is not the goal state because first only we checked it for the goal. Now we need to see that it's also not in the visited list. We have already visited, so that means we need to add it to the visited list or the visited states. And then we basically add the next state to the back of the queue. Okay, and that's how this whole loops, and basically we continue this process again and again, and hopefully we find the solution if it exists, or not hopefully, if it exists it will be able to find it. If your friend exists in the building, you will be able to find it. Now the next algorithm is the depth first search algorithm. Now here let me go to the depth first search. Yes, I don't really like this font that much, so I'm going to stick to this one. See, yes. So what is the core philosophy of the depth first search? It is to just directly go to the deepest level. Okay, means suppose you are, basically the best example is you are in a maze and you continuously follow the path of going right and then going left, going right, going left, going right, going left, but you don't follow. Let's say there is another option, be the third option. Okay, that means you are at a position where you have multiple rooms. You basically choose the first room each and every single time. That means you are going your with that choice of first room, you are deepening your search at each and every iterative level. That's why this is called the depth first search. Let me see if I have it here. Yes, this is the depth first search algorithm. Let me just change the font or the theme to this forest. It looks a little bit pleasing to the eye. So let's quickly kick off the things. Yes. So yeah, I was just giving you this example about you are in a maze. Okay. So the example that I wanted to give you is, suppose you are in a corn maze. Okay. And you basically pick a path. That means you make a choice that I will always continue to the left. You pick a path and you keep walking down to it. You will always like go through that path and your choice, and you continue till you hit a dead end. And when you hit a dead end, you walk back to your last intersection, but you walk back one step before and take the next step, and then you again repeat that main biasness in your head, and you continue till that end of that path. Okay, and you repeat this until you find the exit. Okay, now the point is, you might find the exit quickly, or you might explore for a very long time, a winding path on the wrong side of the maze first. Suppose the answer lies at the end of the maze and you are going through the first part, then second part, then the first, then second, and you go on, and it will take you quite a long time. Now again, okay, there are a few things to mention, which is that it uses the stack data structure. Means there is a stack of books, stack of plates. You take the last of that you inserted, the first thing that you take out. So you push the starting state into the stack and then you loop. Basically, you pop an item from the stack, then check if it's the goal state. If not, then you push all its unvisited neighbors into the top of the stack. Okay, because stack is like from the first, like from the last inside stuff that you put it, you take the first thing out. So the point is that it has a few characteristics that you need to note down. Completeness. No, in an infinite graph or one with many cycles. Cycles mean, suppose it's basically when you have a connected nodes which basically cycle back to one particular node. Okay. The DFS can get stuck going down an infinitely long path and never find a solution, even if one exists. And remember, this is very, very difficult for cyclic graphs. Okay. And one more point is that it's complete for finite graphs. Optimally, no, the first solution it finds is unlikely to be the shortest one. Means it won't find the shortest solution very first. The good point is that it's very low in memory. DFS only needs to store the current path it is exploring, and this makes it extremely memory efficient when you compare it to BFS. Now let's go to the diagram and the problem solution that we have. So at the first step it's like 0,0, then you fill the 3-liter jug, then you fill the 4-liter jug, then you basically, this is the filling algorithm. Then you find that, oh, okay, let me pour down the 3-liter jug, then you again fill up the 3-liter, then you do the pour action, then from 4-liter you do the 3-liter, then you do the throwing out action, basically what do you call this, empty action. Okay, and then after you pour out the water, you have 0,1, basically 0 liters in 3-liter, 1 liter in the 1 liter, then you have something to pour again, so you pour again, then the 3-liter is having 1 liter. Now what you do, you fill up the 4-liter jug. After that you filled it up, then you again pour the 4-liter into the 3-liter. Finally you actually check that, oh, there is only 2 liters left in the 4-liter jug. Now this is the deepening of the path. How does it even deepen? The point is that first you initialize the state. The 0,0 state is added to the stack. Point is the stack empty? Then answer is of course no, because there is something. So you pop the state. Okay, you pop the state which is 0,0, and then you keep on exploring. Again, the same mistake is that this part, this whole thing that you see on the left should be here. Okay, and the point is that suppose you generate the all the neighbors. For each neighbor, basically you generate more neighbors, but here you see that each neighbor that I'm saying now for the BFS, it was like the level neighbors. It's more like now the neighbor which is below it, the child. Okay, so the point is that you then go to the child, and basically you have all this state. Okay, you put all the states into the stack. Now the point is that you check if these are already visited or not. Wait, I think it would be better if I just show you the algorithm, see the code for it, not this one. Yes. So yeah, you create a stack, then this part is the same. The point that differs is that is a queue. We check it that whether the stack is empty or not. Then you get the next state, which is from the top of the stack. For this case, it will be the 0,0. You then take out the current state. Okay, currently I'm at 0,0. Point is 0,0 my goal state? If it is the goal state, then fine. You found the goal state at the very first step. Now, if that is not the case, then you generate the neighbors. Means you generate whoever is like neighbors. Okay, I should actually mention it. It's like your people who are on the same level. Okay, and after you generate the neighbors, for each possible action, which is fill, empty, and pour, you basically apply that action to it. Okay, now you add to the stack if this is a new state. Suppose you filled up. Okay, if I just go back to the diagram again, let me show you. You suppose fill it up. You fill it up, the 3-liter one. Can I again fill up? Okay, I can again fill up. Can I again fill up? The answer is no. Then what should I do? I should empty it. Okay, then I should empty the 3-liter first. Okay, then I emptied it. Can I again do something? Yeah, which is not fill. Because the point is that they are already filled some way. Now the point is that what can I do? I can have the 3-liter jug is completely filled. Then I can do an empty action. Okay, I did an empty action, which is good. Let's go back to the algorithm again to see the flow. The only difference from BFS is adding to a stack. Yeah, that's the only difference that I want to mention. Now, if the next state has not been visited, then again I'm going to add the next state to the visited list, and this next state will be added to the top of the stack. Okay, and this continues till the solution is found. If there is no solution found, remember DFS, if there is a cyclic graph, it might actually continue forever. Now these action needs to be in order. So after you do the, however, I was, I think it was at 0,1. So I was at 0,1. Now what can I do? I can do the pour action. So I did the pour action. Then, okay. Now point is that I have an empty jug. I do the fill action. Now I see that, okay, both the jugs are filled somehow. Then I do the pour action. After doing the pour action, which is from the greater, what do you call this? Capacity, not the greater, the jug which contains more water to the jug which contains less water. Now, while writing the program, I will show you that there may be multiple instances while deciding this part. So, the way that I have formatted it might not actually be the optimal way. Say you do the actions in a different manner. Say you fill it up, then you instead of emptying it, you do the pouring. Okay, and even that pouring will be done in a certain manner. I've done it in that the jug with more water will be pouring that water into the jug with the less amount of water. Suppose you don't want it to be in that case, in that format, then you could actually change it. You could change that. Okay, from the jug containing less amount of water, I'm pouring it to the jug containing more amount of water, but it's still not completely filled. Now, the point of argument is that that kind of doesn't make that much sense. But if you find that in your problem statement, that particular condition, that from a smaller capacity to a bigger capacity, makes more sense to you in your problem that you're doing, then please do so. This is like more about freedom. You could actually influence how the program will behave in the solution that you develop. Now, the last one would be iterative deepening. Now, we have already discussed about the breadth first search and the depth first search. It might be that your breadth first search, like, consumes up a lot of memory. Your depth first search might be, let's say, faster or slower depending where your node might be. Why don't you combine the two algorithms? Basically, you take the breadth first search algorithm, and instead of like doing a searching at each level, you do a depth first search first at each and every node. But what you do is that at that point in the node, you do a depth first search, which is a limited depth first search. Means you're not going to do it infinitely. After, let's say, you explore 5 levels, you are going to stop. And then you move on to the next neighbor. Neighbor means on a like in the breadth first search, you are again going back to the first floor to find a friend, and again doing the checking out the rooms on one particular hall. Okay. Now the point is that how do you implement this, and how okay, so I think I have made one example of it, which is like a search and rescue operation. Suppose I go into the first example that I gave you about your friend, and it is the friend algorithm. The analogy might not hold up that well, or it might, depending on how you frame it. But this is a different framing where you have a rescue operation that needs to be conducted on a collapsed building. So the point is that if you do floor by floor search, suppose you miss out on some particular rescue, like people to be rescued on the first floor, then the point is that should you go, like after doing the breakfast search, there is a probability that you might actually have missed out. So then you go to the next floor. Now, what do? You can again do a depth first search. You basically go up to the floors and check each and every first room of the floor again and again. But remember, rescue operation is very much time limited and you need to do it fast. So that is not a good option as well. What you do, you just at the 0th level, you search only the ground floor. At the first level, you again go and restart from the ground floor, and after that you again search the first floor. Then on the third floor, you basically do the not the third floor, I think, yeah, first floor, second floor, yeah, sorry, second floor. You restart again from the ground floor, you search again the ground and the first, and now the second floor as well. Now the point is that this might actually seem repetitive, but it actually ensures that they will find the survivor at the lowest possible level. Now I might need to basically pause the video for a few seconds. Yeah, so let's get back to the point. Okay, I am getting again at one. Okay, so let's get back to the point. Let me check its recording. Yeah, I might not be removing this simple 10-second interruption. So the point is that you are able to search each and every floor again and again to find the survivor on the lowest possible level or the shortest path without needing a huge team to search all the floors simultaneously. Okay, so see this is the shortest path and the lowest memory path. Okay, that's why it actually works quite well. Now it uses a loop that controls the depth limit. Means at one point you will only search for, let's say, 2 or 3 floors. Now inside that loop it performs a DFS, okay, a depth first search, but it's not allowed to explore any further than the depth limit. Like I told you, now you basically have a limit to the DFS that you do at the each BFS level. If no solution is found, that means the depth limit has to be increased by 1, and the entire DFS process starts over from the beginning. Now the point is that yes, it is complete just like BFS, and optimal. It is actually very much optimal because it explores level by level and it finds the shortest path just like the BFS. The point is that it is actually low in memory, not very low, I should say, but it is quite low in memory. Okay, since each iteration is a depth limited DFS and it has some excellent memory profile, just like DFS. And this point was taken from Geek for Geeks and all this. Okay, so they mentioned that it has very much good, excellent memory profile. In my testing, I found that it is somewhere in between DFS and BFS, and there are also various other searching algorithms, but it is good. It is really good and efficient. Okay, it actually blocks the caveat of that circular loop with the DFS. Okay, now let's see it in a flowchart manner. So yeah, this is that. Suppose you start with 0, then you basically explore 0, means that you fill the 4-liter jug. Then see here, see something very carefully, that this is the run 6. That means it has already performed runs 1 to 5, but it was not able to find that particular run. So how that run actually works, you set the depth limit to 0, which basically means a BFS. Okay, then you run the depth limited search, or the DLS, means you do a basically a DFS, which is 0 level DFS, which is basically a BFS currently in when everything is 0. Point is that, have you found the solution? The answer could be yes or no. So the point is that if you found a solution, then great, that's where it ends. But suppose you haven't, then you increment the depth limit. Point is that when you increment the depth limit, what actually happens? Wait. So you start with the DLS with the current limit. Suppose it is now 1. Okay. So what you do, you use a stack just like the DFS. Okay. Now after that, you basically check that is the current depth less than the depth limit. Of course, for a first iteration, it should be. Okay. Point is that you could be using less than equal to, and that depends upon how many DFS you want to run in one particular BFS level. Point is that stop this path and backtrace if you are unable to particularly find the solution. And suppose so not sorry, if the current limit is less than, then of course you need to stop here. Means you have already reached the limit of how many DFS searches or how many levels you could explore using a DFS. Now you need to stop here and backtrace. But suppose your current limit is less than the DFS limit, you are able to go and continue. So that means now you do the generate the neighbors, just like in BFS, you check the level. Okay, in that particular level, how many neighbors or neighboring rooms do you have to explore? Now, after you generate the neighbors, you again add the neighbors to the stack, and then again basically look for the solution or the answer. Now, this is the generated path. Okay, that you basically run for. See, the limit could have been 1, 2, 3, and 4, and we did it till 5, and no goals were found. Then only at the limit 6, the answer could be found. And I'm not going to go into the each and every step. You have already gone through this multiple times. The point that we can explore more is the pseudocode here. Now you start with a depth limit of 0 and increase it indefinitely for that limit from 0 to infinity. Point is that, does it make sense to put it at infinity? No, you should actually have some limiters, because at some large value enough, your search will not actually make sense. And there are algorithms to switch from ID-DFS to other algorithms after that limit. Okay, means it's not basically feasible to search using DFS at that point. So first you do the depth limited search for the current particular limit. You basically check if the solution is found based on the call the depth limit search. Okay, so this is the depth limit search operation that you need to perform. How this is performed, we are going to basically be like a C programmer, and after just seeing that function, we will jump into this. What does it basically mean? This is the function. Oh, by the way, if you are seeing this for the first time, how algorithm is written in a algorithm, you need to specify this specify this keyword, which is function. Then you write the name of the function. Okay, and something happened. Just I don't know why. Just Okay, whatever. So now you write the name of the function and there are function parameters in that particular first brackets. Now first you create the outer loop for the depth, which will start with the DLS or the like depth limit searching limit of 0, and you increase it kind of indefinitely, but I'm again saying there is a limit, which you will do after you learn a lot of different algorithms. Now you do a depth limited search. Okay. So here what we do? We create a stack. After we create a stack, we also create a list to check out the visited states. Just like in BFS, we need to have this. Now in this stack, we first insert the state 0, 0 and with the depth 0. Add all this to the stack, then we are going into the main loop. So while the loop, so the in the loop is checking that if the stack is empty or not, then the current state, you are going to basically remove it from the current state, remove it from the stack into the current state. Now you need to check that if the current state is the goal state, and if it is the goal state, generally the 0, 0 is never the goal state. So we need to continue. If not, if the 0, 0 is not your goal state, means the trivial condition is not that, then you basically check if the current state is your goal state, you reconstruct and print the path, else of course we need to continue. This is where the depth check needs to happen. First you check that the current state's depth at which it is currently is it less than the limit or not? Is it less than or less than equal to, depends on how you want to frame the algorithm, but how many depths you want to allow. If it is less, then of course for each possible action, that means it could be your fill action, empty action and a pour action, you go to the next state by applying that action in a order that you have already defined as per your DFS algorithm. Now if the next state has not been visited, now you need to, after you generate the next state, you need to first check that have you already visited it. If the answer is no, then only go and check for the solution in that particular state. Now you need to add this next state to the visited states and add it to the top of the stack. If you add it to the top of the stack, it will again go into the main loop and check for it. Now this is basically what? This is nothing but your DFS algorithm, right? This DFS algorithm is now having just one more condition, that how many times it could actually run it. Now after this is called the depth limited search, you go to the breadth first search type of algorithm. Now here, if you find the solution, then it is great. Otherwise, basically you need to increase the depth and do it for the next neighbor. Now if the solution is found, then basically the DLS function will have already printed the path, so you don't need to worry about it. But suppose even there is something like what do you call this? Yeah, if the solution exists, then it is guaranteed to find it. Okay, that's the main point. But suppose if the solution doesn't exist in that particular search tree or the search graph, then you are not exactly doomed, because the DFS is now limited. So it will just say that no solution could be found for this, means it is complete. But in DFS, there was a possibility that it could loop back to that particular state again and again in a cycle. So even if the state exists, it won't be able to find it. Or if it doesn't exist, then, and if there is no cycle, then only the DFS searches answer that no solution exists is quite believable. Okay, so now that actually concludes the theoretical understanding of the three main algorithms. In the next video, I shall be programming all the stuff or the algorithms to solve this particular problem, which is the water jug problem, as already narrated here. So that's the end of this, and goodbye.